Thank you, Barna, and thank you all for coming. Thanks for the very generous introduction. In fact, my biggest honor is probably being the inaugural speaker at the College of Computing's Distinguished Lecture Series, for which I'm eternally grateful for this invitation. So today I'm going to be talking about some area of work. So by way of introduction, if it wasn't clear from Barna's introduction, I am a theoretical computer scientist, and my work is in theory. But that doesn't mean that that's the only thing that I'm interested in, and I'm going to be deviating from some of the questions that usually the theory of computer science has asked, and digressing into other areas, but still with my own theoretical perspective. So that's the perspective that's going to be working behind the talk, and I'll tell you about this area of work. First thing I'll acknowledge is that most of this started off because Brendan Juba was a graduate student at MIT. He'd been working with Manuel Blum as an undergraduate at CMU, came to MIT and said, I'm looking at all of these questions that you're looking at, but they look so pedestrian to me in a sense. So he said, I want to do something which is different. I want to understand some questions which are not so easy to analyze under the current lenses of theory of computing, and let's go beyond that. And that started me. We had to rack our brains together and to try to come up with some questions, and led us to this area which I think is very promising, where we are definitely able to point to some intriguing questions, and by now even see some interesting phenomena emerging, but certainly nothing close to a full picture, and nothing so close to even the right answers or something. So I'll try to tell you a little bit about this, and there's a lot of people that have joined us in this line of work as we worked along over here. So let me start with the very basic contrast that I want to start working about today, and this is the contrast between communication and computation. So these are two really intriguing components on which our technology relies on today. But how did we start in this area? So firstly, it should be sort of immensely clear that these are two technologies that cannot survive without the other. A computer cannot exist without a good communication platform within the computer to take information from the memory to the bus, or to keep memory preserved reliably. And on the other hand, computation is inherent, storage of information and information in general is inherently noisy. It's going to, in order to recover from the noise, you actually have to design good algorithms and good mechanisms to fix the errors. So these are very interdependent, both in terms of technologies and in terms of the theories behind it. But if you look at how these things have evolved over time, the technology, think in the pre-1990, every company that you talk about was either doing computing or communication, but never both. Maybe neither, but definitely very rarely both. And the products were similarly developed. They were very, very separable. The commerce, most of the models for business models were not really built on integrating the two entities together. And over time we realized that each one of these, a communication device can actually do some computing and may be useful. Maybe it was originally just a calculator put into a phone, but by now every phone is very, very sophisticated as a computer and can do every task that a computer can, maybe a little bit more slowly. And vice versa, every computer is built with a huge collection of ports going out, and these are all allowing it to communicate with the outside world. The theories of these two areas is what I want to talk about a little bit. Were developed in, okay, this is a little bit of a, I'm sort of pulling out just two highlight figures. Turing in 1936 wrote the seminal paper which told us about the existence of a universal computer, and that gave us the model of this one computer that can be programmed to do arbitrarily other things. Shannon in 1948 wrote this seminal paper called The Mathematical Theory of Communication. It actually took 4 years for him to write this paper, and it pretty much provides the platform for what is it that we expect a communication device to be able to do, a communication system to be, and it tells us what it means for it to be reliable and efficient. Now, the thing that I want to talk about today is that these are sort of theories that have been well separated by a brick wall. And they've really, from the beginning, this is the way we've sort of worked with it. Turing assumed perfect communication between, perfect storage, perfect communication. Shannon assumed, you could build computing function, you could compute any function you wish. And that was it. They never looked at each other for the longest of times. Not truly, both individuals probably looked at the other side for a little bit, but the theories never did. And this, I claim, is actually a little bit of a detriment to us today, because today we are in an environment where every device is actually doing both communication and computing. So it's putting us in a very different scenario. The computing theory and the fundamental principle there is universality. You can program your device to do whatever you want. You can go to the store, buy a Mac, and make it look like it is a Windows machine if you want. I mean, if that's what you care for, you can actually do it. There's nothing to prevent you from doing this. You can program your computer to look like anything you want, and it's not that we actually take it from one well-known system to another one, but actually each one of our devices is looking slightly different. If I look at my cell phone today, by the way, I bought this cell phone 3 days back, and then I had to return it because it was apparently a Verizon phone and I needed an AT&T phone. I went back and bought the AT&T one 2 days back. Looks completely different once I turned the power button on. They don't do the same things. There are no two devices in the world that actually are identical. And I thought that was only after I owned it for 1 day, but it's even before that. Okay? You can program your machines to do whatever you want, and these are communicating devices. They don't look identical. So there is a heterogeneity of devices. The communication theory, on the other hand, Shannon's theory, really builds on this paradigm of saying, I understand that I'm going to overcome this channel. This channel is the adversary. This is what I'm trying to overcome. So I'll put in two things, an encoder on one side and a decoder on the other side, which will together jointly overcome this thing. Okay? So it really believes in a central design principle. The two endpoints have to be designed together, and if I want to go out there, sell out 1 million cell phones, I'll put the same platform on all of these. So somewhere out there in this machine, there is an entity which says, this part better be common for all the devices, even though some other part, and I cannot even see the part which is common for all the devices, the other part is completely variable. And yet these two layers sort of percolate and leak information between each other, and they start introducing errors and so on, and every once in a while I suspect this machine will say, okay, I need to reboot and I'm not going to react to your changes, and then somehow rebooting works out. Sometimes it's become so complicated it doesn't work and I have to throw it out and get a new one. So there is a contradiction between heterogeneity, that is the assumption that computing theory sort of wants to or a deliverable from the computing theory that we want to enhance. We want to say everybody can program their machines to do whatever they want. We'll sell you one device, you can make it look like anything. And the homogeneity that the communication infrastructure needs to work on. So these two are a contradiction, but does it really matter? And the purpose of this talk is to say, yes, it does matter. And then we will digress into sort of, some theoretical questions that come from this diversity, a model for studying this diversity, and then some solutions for studying this. Okay, I must say, even if you're not convinced with the examples that I come up with in this talk, I hope to at least convince you that there is something very important going on between this divide, and we can't just afford to stay away from it and say, oh look, there is no theory that will capture this, and we'll just have to live based on ad hoc designs and things. If you have good ideas, then there should be a theory which captures the good ideas and tells everybody that's a good idea. So there should be something to seek over here. So here are some opportunity costs, some problems where I think it'll be great to have better communication if we could do this. I go to a friend's house, there's a printer out there, and I say, look, I need to print something. How do I do it? I actually ship them a PDF file and then they print it for me. I mean, why can't I just go from my computer and say, look, here's the printer, figure out how to print on this printer and do it. At the very least, you have to sit down, babysit your computer, add a printer, etc., till you get it to the point where it can print. It's not the same as printing at your own home. But this is a pretty intelligent computer that I have. There's a very intelligent printer out there also. Why can't they just talk to each other and resolve it? I think there is a sort of a missed opportunity in the sense that these devices are not doing communication according to the principles that we expect. I mean, I don't go to a McDonald's or a Starbucks and say, okay, let me call your CEO and find out how is it that I should order something over here. I go out there and I figure it out. Even if I've never been to the store before, I know how to go talk to the people out there and figure out what it is that I can buy and how to buy it. Why can't we do the same thing with two computers talking to each other? If I'm projecting from a laptop today, I didn't have a problem. But if I had a problem, and so far we have not had a problem, it's remarkable. I mean, I think we seem to be over this hump, but at least 3 to 4 years back, every talk, you give about 10 minutes of the talk to setting up the projector. And if you want to have a series of 10-minute talks in 1 hour, that means you'll get 0 minutes of talk time. Okay, so so you really would love to say that, look, the projector is a smart device, the computer is a smart device, figure it out, project what I want to project. It's really hard, and it's still not there. Here's another problem that actually is of the same vintage. I would love to have this idea that, there is this idea we're taking all our information and digitizing it, but what is our confidence in the fact that this digitally stored files that we have out there are going to be readable 100 years from now? I mean, when I wrote my PhD thesis, it was, it was clear to everybody that PostScript is the medium in which you store your files, because this is the one that's going to be readable forever. And now out there, I go and click on a PDF file, and my computer tells me it doesn't know what to do with it. And even PS was considered a wasteful way of doing it. They would say, take your PS file and then gzip it, and that's the right way to store it, because who wants to pay all this bandwidth in order to communicate it? So many people actually post compressed versions of their PostScript files on their websites, completely unreadable today. I mean, it's it takes me more than a minute. I don't read it. So I'd love to have a schema by which I say, here is some piece of data, and I've put enough redundancy into it such that 2,000 years into the future, somebody wants to click on it, they'll be able to click on it and read it. Is such a thing even possible? What would the theory be? How do I react to the uncertainty of the future? 2 questions. Let me start with you first. Sridhar.
So, in terms are interesting enough. The Library of Congress did a study on what they thought was the most survivable long-term medium, and did an exhaustive comparison of digital and analog technologies. And they concluded it was the vinyl record. The only thing that they could guarantee would be readable 1,000 years from now.
I mean, I think in terms of sort of reliability of the physical medium, maybe. But I could bring you a vinyl thing today and send you scurrying around the building. This is the building of the College of Computing and Information. Play it for me within an hour, and we're still going to have a challenge. Yes, question there.
So you can go to a Greyhound bus station and print your ticket with your arm finger thumbs and airplane with like on their fingers. But I think that wasn't the examples like those under your point. Maybe you could connect it at a deeper level to the contradiction point in the previous slide.
Sure. Yeah. I think the reason most of this diversity is most of this complications are happening is there is a uncertainty. I don't know a priori what this printer, what format it might want to take. The printer, on the other hand, a priori doesn't know what format I'm going to be sending the files in. Until we manage to agree on the 2 things, we are not able to communicate. So determining what is the format that we should use for the other end, determining what it is that the other end wants, what format it would want in. Once you tell me what is the format in which this printer wants the header or the tail or whatever, it's easy for us to get to the point. So I can eventually print from my laptop onto any computer in this building, but it just takes me a large amount of prep time. And it's not even the time that I worry about, it is my time that I worry about. It is mechanical work. Why am I required to do this? Okay, so that's a great question. In fact, hopefully I'll try to get to it in the next couple of slides. Any other questions? And by the way, I do encourage questions as we are going along, because if we don't, then it'll get into the point where I'll be telling you about things that you don't want to hear. So the only way you can rescue, save yourselves from that situation is ask me questions.
So so part of what you're describing is it's just the format, but there's also the authentication issue.
I'm not worried too much about the authentication, or at least I'm not focusing on it. There is certainly this question of who has the rights and the privileges. I think we have a better handle on this. What we don't have a handle on is the initial part of handle, in the sense of understanding what is the question and the answer. We don't have a great understanding of the question of what it is that I need to do to be able to get to the thing. When do I know that things are working well? When do I know that things are not working well? Those are things that we not modeled very carefully. Okay. So the essence of semantics, I would say, is uncertainty. This is more or less answering your question. And this is something that Shannon very nicely encapsulated and shoved away. Okay? He said the significant aspect is that the actual message is one from a select set of possible messages, and that's all that we care about. So once we agree on the set, and this is a set of messages from which I want to send you one, and we agree what is, each one message, what is the meaning of each one of these messages, the only thing that remains is I have a message and I have to send it to you. We can do this somehow. But the thing is that what is the set of messages that we should be talking about at this stage, and what does each element of the set mean depends on something called the context. And this context is something that we shed, we swept aside, but that comes in and plays a significant role. So context in human communication is referring to things like the dictionary that we rely on, the grammar, the general knowledge, etc., etc. All of these things, they guide our communication. I'd say more than just guiding our communication, they allow our communication to be short today. If I had to explain to you what are the rules of English, what are the rules of mathematics, what is the tradition of history in computer science, all from the beginning, it would take me 3 or 4 years. I can get something interesting, I can say something interesting in a talk today because I can rely on this context. Okay? So in design systems like computers talking to each other and so on, there is a similar context. What is the coding scheme that is being used, encoding and decoding? What are some prior distributions on the messages that we may be all relying on? What are some communication protocols that we are relying on? All of these are part of the shared context. Now there's a big difference between how these two settings, the human communications and the other setting works. The context is always huge, something so large that we don't even want to talk about it, but it's not, in the first set of examples at least, we cannot assume it's shared perfectly. Okay? We don't have the perfect synchronization on the English dictionary, and that's the simplest of the problems. Grammar, we can also tend to do a little bit of give and take. General knowledge, certainly we don't know all the same things, but somehow it's still playing a very useful role in this communication today. Can we see and extract this kind of information and use it? And standard theory of the Shannon-like theory has tried to use information like shared context, but it assumes that it's shared perfectly. And then, of course, it sort of just gets swept away. You know the context, I know the context, there's no need to talk about it, let's just go ahead. But it's not shared perfectly, and that's where much of the interesting questions arise, and this is the kind of questions that I try to talk about. This is not a most brilliant slide that I've come up with, but this is probably the most important slide that I can give you today. Okay? The classical Shannon model had a well-known entity Alice and well-known entity Bob, and the two of them were talking to each other over a channel. This channel was the malicious element, that's what we were trying to overcome. But today I'll sort of sweep the uncertainty introduced by the channel. Let's assume we have a perfectly noiseless channel connecting the two of us, but I don't want to assume that there is this Alice and this Bob. Instead, there is this cloud of possible Alices. All of these Alices are my device with various different flags tweaked one way or the other, or all the members of this audience are the various possibilities for who all Alice could be. All the possible speakers who could be out here giving talks are the various possible Bobs. Okay? And now this channel is coming along and saying, okay, I don't tell you which one of these people is going to be put on this endpoint of the channel. I don't tell you which one of these people is going to be put on that endpoint of the channel, but we're going to do this. So AK is going to talk to B2. That's what's going to happen. But it's up to the two of them to figure out in what ways this person differed from amongst the various people in this entity. How did this person differ from the various people in this entity, and put the two of them together and says, now start talking. If there was a notion, classical models, I would say, would pick Alice 1 and try to get them to talk to Bob 1. Alice 2 would talk to Bob 2. They are all speaking the same language, or they have the same context. The subscript can be thought of as the different contexts. And we will usually not pick arbitrary elements, but there will be some relationship between the left and the right hand point. But the relationship will not be a simple matching, saying, you know, as soon as I selected you to speak, you will be speaking to your matched partner on the other side. That's not going to happen. Some uncertainty about who you're going to be talking to, and then can you try to achieve a particular goal of communication in this setting. This is the kind of model that leads to a large collection of beautiful questions, and I'll give you 3 vignettes of questions that arise in this model and the kind of solutions that we solved in this model. In each one of these cases, I will try to tell you what the question is relatively crisply, and then try to come back to this model and say why it actually fits as part of this. It may not be a priori clear, but I'll try to say that. And the hope is really, I mean, we want to have a better understanding of existing mechanisms. There are lots of examples in natural communication where we have mechanisms which overcome this uncertainty. I don't know who I'm talking to, but I managed to, you know, I don't know what languages you speak, but I managed to extract directions on how to go to a cafe, coming here and asking you. You know, I don't have to know everything about the UMass campus in order to be able to figure out where to go. So how are we able to solve these problems? That's one of the questions. And then, you know, we would like to say, look, okay, very often we can actually design solutions that work very nicely, but we don't know what is the definition of working and what is the definition of you know, being a correct solution or a good solution. So what problems are they solving? What are the, if I give you 2 different solutions to a problem, which one is a better solution? These are the kinds of things that we would like to understand. That's the eventual goal, but now 3 vignettes in this setting. Okay. The first of these vignettes is what I call the uncertain compression problem. Okay. The way we came to this question was we were trying to understand, this was work done with Brendan Juba, Adam Kalai, and Sanjeev Khanna. We were all, the 3 of us were at Microsoft at the time, and Brendan was a graduate student at Berkeley, at MIT. And what we were trying to understand was, you know, this human communication has this very strange dictionary that we work with. We wanted to understand why it was like that. So what is strange about a dictionary? Well, a dictionary says, if I want to send you some particular message, some meaning in my head, and I want to communicate it to you, it says, here is a word that could say that, and here is another one, and similarly M2 has W21, W22, and so on. There's a huge list of possibilities. I can send you, I mean, it may not even be a word, it may be a phrase, it may be a paragraph, it may be a whole page. But the language, let's say more generally, tells you how I can communicate certain messages. So why are there multiple messages, multiple words that I can use per message? But even more importantly, when I look at different messages and yes, look at some of these words, they might actually appear in multiple places. This word has multiple different meanings. Why did we do that? Why didn't we pick an injective map? Okay. Why are we doing this? So this is what we were trying to understand. We said, look, okay, there seems to be some natural reason. These words I could sort of, let's say, sort them in order of increasing length. And why would I not use the first word that appears as a possible word for this message? It's because maybe it may be confused under the current context and you might think I'm talking of something else. I talk about the word phrase IP. Well, it really depends. I mean, are we talking to a bunch of networking people? Are we talking to a bunch of mathematical programming people? Or are we talking to a bunch of lawyers? I mean, in each one of these cases, there's a different meaning associated with it. I would not use the phrase IP in a broad audience like this, but I might use the phrase IP if I'm very sure that I know who you are and what you're thinking about. Okay? So we have these different things. So can we try to, you know, justify this kind of a mechanism? What's the setting and how do you do it? So we said, okay, look, okay, clearly the context is the important thing, and the way these, you know, encoding the scheme which says in order to send a message, how do I send it? The way it works is it takes the message and tries to find a shortest unambiguous word in the current context. And the way the decoding works is that given a word, it'll say, yes, Luz, how do I say which? So I've given you this word W32, but of course it also appears as W11 and maybe W45. Which one of these things does it mean? Well, I say, well, I should decide based on my current context. So this is roughly what's going on. So, but what is context? So, of course, this could open up a huge can of worms if you're in a communication studies department or something, or in a linguistics field, fortunately will abstract away most of this question and just say context just tells me what is the probability distribution currently. If I give you the word, ABC, what does it mean? If I give you the word IP, what is the probability it stands for intellectual property? What is the probability that it stands for internet protocol? And what is the probability that it stands for integer programming? Okay, I'll tell you these three probabilities. Depending on different contexts, these probabilities are going to be very different. And what should you do as a decoder is to say, well, okay, I know the current probabilities. If this person says IP at this moment, because the most likely event is you're probably talking about integer programming, it must mean that. Okay, so I would just take all this context and measure into this probability distribution. Okay, so what context is telling me is it's telling me a probability distribution. So if this is what context is doing, what should the hope be from a good dictionary? The good dictionary should be able to compress a message down to the entropy of the context, right? I mean, that's what we would hope for. So can we prove that the English dictionary achieves this property, that it takes some measure of entropy and reduces things to the common thing? Of course, this would understand deep knowledge of the English dictionary, which I don't have. So instead, what we will be able to do is analyze the random dictionary. That's what you do in theory. You come up to a point and then you say, okay, look, at this stage, we need to create a very simple model to illustrate the principle. So that's what we're going to do. So now, but an ideal dictionary would compress things down to the context, but that's assuming the sender and receiver have the same context. But even better than ideal would be this kind of a property where you say, well, I don't know the context that you're working with. You don't know the context that I'm working with, but we know that we're more or less working with the same context, which means your distribution is more or less the same as mine. And even then, when I compress according to my distribution, my context, and you decompress according to your context, it should work. And this is where this notion of this uncertainty comes up. There is the sender, and the sender's context is all these different probability distributions. There's the receiver, and their context is all these different probability distributions. But you are not talking to the person who has exactly the matched probability distribution. You're talking to somebody who has almost the same context, which means almost the same distribution. And now can you make some things work? That was the question.
Will the message be used to figure out which context you're using?
No. Will the message be used to figure out which context you're using? Not in our model, but in the right way to think about general communication is it's a random walk on context space. So I have a particular context right now. You give me a message. It not only, I have to you give me a word, let's say in my language, a word. I decompress it into a message based on my context. And then I say, okay, based on the fact that you send me this message and I was at this context, I'll now update my context. Okay? So I will not talk about this evolution process. I will just talk about one step in this whole thing. One message from you. I use my context. I use the word that you've sent. I figure out what's the message. Any other questions? All right. So this is what should happen. And so what will we be able to prove? If the dictionary is really random, which means each one of these words happens to be random, you say, given the message M1, I'll send you a random bit. That's the 1-bit word that I could use to describe it. Another pair of random bits, that will be the 2-bit word that can describe it. Another random word, which is the 3-bit word that can describe it, etc., etc., etc. And then you apply this natural encoding and decoding principles, which says, given a context, I'll use the most unambiguous word which represents this thing, and you can formalize that mathematically. And similarly, when you're sending when you're receiving a word, you say, well, let me see what is the most likely message that could have been associated to this word under my context. If I use the two, this actually works as a great compression scheme, compresses information down to its entropy. The entropy is the limit, even if the two of us agreed perfectly on the context. But even without perfect agreement on the context, you can actually do it. And it will manage to get good compression, entropy of P plus some factor which depends on the distance between my and your context. And this definition of distance is something that I won't describe today, but you can actually have my distribution being significantly different than yours and still manage to get compression going. Okay? So this is the kind of a question which I think fits this paradigm. There is uncertainty between the sender and the receiver, and we are designing communication schemes which work even though we are not perfectly synchronized. And in fact, one of the nicest things about this kind of an example is we don't spend all our time trying to figure out, oh, you could be this person or that person or that person. Let me spend some time to figure out which one of these you are. And then let me send the message that I want to send. That would have been extremely inefficient because my distribution is some, let's say, n bit long, n element long sequence, n bits long. Your distribution is some n bits long. We could be differing in every coordinate over here. Resolving the differences like n possible things of communication. If I just sent you the information ignoring the distribution, that would take me only log n bits of actual communication. You can actually, so overcoming the differences in our context would have been futile, and we don't have to do that. We can just go ahead, realize that there's going to be uncertainty between the two of us, and build a compression and decompression scheme based on that, and it works. Okay? So that was the first of the theorems in this part. This is where we got started with these kinds of questions. Okay? Any questions at this stage?
So I guess I'm confused because it seems if I have a random dictionary and you have completely different...
Oh, I'm sorry. Good. Okay, so I'm going to assume that the dictionary is shared perfectly between me and you. Okay. What's not shared perfectly is the distribution. The dictionary is shared. This, I mean, as soon as you sort of brought up the question, oh, this is something that also struck us, and we said, we are assuming that there's this perfectly shared dictionary between the two of us. Can we overcome this? And we spent some amount of time trying to do this, and I'll probably get to some of those questions. It's not as trivial as we would have hoped for. So anyway, so some of the implications that I want to highlight is that there is this tension in natural communication between ambiguity and length of the conversation. Okay, short conversations tend to be ambiguous, longer ones tend to be less ambiguous. Is there a mathematical model which explains this? This was the model that really explains it, and this is, as far as I can see, it's a very compelling model. It does reflect this human communication. This shared randomness assumption, which Neil unfortunately brought out, is a very debatable assumption. We tried very hard to overcome this. We tried to say, well, maybe we should study the dictionary, but this is really very hard as a question. The other thing that you could try to do is somehow come up with this dictionary deterministically. You start off with zero information, you look at your context, and you say, how should I start communicating? It's not ruled out, but there's no solution out here either. So we did the next best thing that we could under these circumstances. We said, okay, so far we assumed that the dictionary was shared perfectly. Let's at least make it, imperfectly shared. And this, of course, is a theoretical model. So it's, already the fact that the dictionary is random is very theoretical. The next notion of imperfectly sharing is going to be even more so, but leads to a lot of very intriguing questions. And I'll talk a little bit about it. In general, there is this notion that there is some randomness being shared between sender and receiver, and what happens when it's imperfectly shared. Okay, there are many communication settings in which using randomness between sender and receiver can be beneficial to the communication, but how does this change when the randomness is not perfectly shared? We are looking at some sunspots to determine the randomness. We're both probably paying attention to the same things, but we both have some noisy reading of this thing. How does it affect things? So this is vignette number 2, imperfectly shared randomness. It also fits in the same paradigm. There was some communication where you could do things when a certain element of context, the randomness, was perfectly shared. What happens when it's not? Now, in getting to this point, we also made a following realization, which I want to share with you, which is that we tend to model communication by the Shannon model, but there is an alternate model under which we could be looking at it. And that's the model that I would be trying to look at. So for example, compression problem was a classical Shannon problem. You're given some message X, which is distributed according to some probability distribution P. and P sub i's denote the various probabilities of the n possible messages. And but we could also ask the question, what is Bob going to do with this message once it receives it? Okay, and often knowledge of this entire string X is overkill. Typically what Bob wants to do is, he also has some private information Y. What he wants to do is something which is dependent on the message that is sent from you and the message and the information that he already has. It's some joint function of X and Y. And this is a model that was that was studied by Yao in the 1980s. And it says, okay, if you want to only compute f of x, y, then maybe you don't need to know all of x in order to do this. Okay? Can we get away with much less communication? And the general Yao model allows interaction between Alice and Bob. For the most part, I will talk about only one-way communication. Alice sending some information to Bob, and that's it. But we can talk about it in the other setting also. Now, very brief. So very quick thing. I mean, what are example problems where you could, very little communication satisfies? Maybe X is an n-bit string, Y is an n-bit string, and what we want to know is the parity of the bits of X and Y. Okay. Well, clearly, in order to compute this, Alice just needs to send me the parity of the bits, her bits. She doesn't need to send me the entire n-bit string. Okay. So clearly, there are existentially problems like this where very little communication suffices. It depends on every bit of X, but that doesn't mean Alice has to send every bit of X. But this is a kind of a trivial example. All of Alice's inputs could have been divided into two equivalence classes, and she's trying to tell me which one of the equivalence classes she lies in. She knows which class it is in. So there are very few such problems deterministically where you can do this, but if you include some randomness, Alice has some randomness, Bob has some randomness, there's a huge collection of beautiful problems where you can actually get away with very little communication and compute some joint function of X and Y. The prototypical example over here is the equality. You have a string X, I have a string Y, and we want to know if the two strings are equal or not. And if we have some shared randomness, then we can get away with a constant number of bits of communication and get constant probability of correctness. And the important thing about constants is it doesn't depend on the scale of the universe. So, as long as we've agreed on how to represent messages, it doesn't matter how large, I might choose a very, very, very wasteful representation of, we might choose collectively a very wasteful representation of messages, doesn't matter because representation is independent. I mean, this is constant number of bits. If my information equals yours, we will say, we will agree on this. If they're different, we'll realize this, and it'll take constant amount of communication to get to this point. So there are lots of interesting communication problems where we can get away with very little communication, much less than shoving all my input over to your side or vice versa. Can we do all of this? And in particular, this works very well if you have shared randomness. You have some random string and I have it exactly. How much of it could we have achieved with imperfect sharing? Imperfect sharing is, I think, it's an interesting theoretical question. It's not probably the most natural question out there, though. I mean, if you look at how file systems check with each other if they are synchronized. I mean, I have this mothership over there and I have a copy of this data over here. How do we check this? It's this equality checking protocol that we run. And it would be great to know that this equality checking protocol relies on some common randomness. Doesn't have to be exactly the same common randomness. It will be slightly different, and it's still, there is a protocol that will work. Not the one that you're thinking of, but a different one that we've given. So this is an uncertainty motivated question. And let me tell you a little bit about what's known over here. Communication complexity, even if we don't share randomness, but if we are just randomized, is going to differ from the communication complexity with shared randomness by only a plus log n factor, okay, where n is the length of our inputs. Unfortunately, it depends on our representation of inputs, n. So it really is something that we would like to get rid of. So additive cost of log n may be too much. In fact, in things like compression, where the n describes the size of the universe, so that the probability distribution is described by some n log n bit string, log n additional bits is just huge. Okay, it's worse than trivial. So we tried to understand what would happen with communication complexity, and this was a model that was recently studied by Bavarian et al., and then we independently started looking at this and then came up with similar answers and some strengthenings. And what they were able to show is that actually equality testing, testing whether you and I have the same string, can be carried out even if our randomness is imperfectly shared. Let me explain what does it mean to be imperfectly shared randomness. Randomness, we'll assume, comes as a sequence of bits. This is going to be a very representation specific notion. Perfectly shared randomness means you and I get the same sequence of bits. Imperfectly shared means I get each bit noisily flipped, not adversarially, but by a random process, stochastic process, independently with some probability. As long as there's correlation between your randomness and my randomness, this result works. There is actually a constant bit communication protocol. So this is really like, this is what we do hashing for, and hashing actually works with all its glory, even when the randomness is not perfectly shared. The randomness used at the encoding stage does not have to be the same as the randomness used at the checking stage. Okay. So we started doing a very systematic investigation of this thing, and we realized that this was actually, if you go back to our compression problem from the previous thing where the distributions were not identical, and you also threw in the dictionaries are not identical, but they're random but correlated and random, then actually you recover the communication complexity result. You actually can compress with down to length which is proportional to the entropy plus the distance of the distributions, the distance between our contexts. There is a constant factor in here which depends on the level of correlation. The weaker our correlation, the larger the constant, but that's what it is. Okay? So if the randomness is not perfectly shared, then you have to pay a penalty, but that's affecting the constants in front. More general result that we were able to show was any communication problem that I could solve with some k bits of communication. Doesn't matter how large the size of the universe. If you do need k bits with perfectly shared randomness, you could do it with 2 to the k bits with imperfectly shared randomness. So this is a special case of that result, by the way. I mean, order of 1 was a constant, 2 to the order of 1 was another constant. We didn't notice the difference between the two constants because we didn't explicitly write down the constants then. But if you actually wrote it down, it's really going from 2 to 2 to the k to 2 to the k. And it seemed very weak, and then we did we were working very hard to improve this, and unfortunately failed by proving that a lower bound of 2 to the k was actually out there in this thing. So it was a very interesting phenomenon. Somehow imperfectly shared randomness does lead to a cost, but it's not an essential cost. But still, to me, actually just the positive result is great, because there are many problems that we can think about where good, strong algorithmic results are known in the positive sense, and the fact that you can get away with constant communication is, I think, sort of a very nice story. For most problems that we were able to, that we explicitly pulled out and tried to solve, we could actually get much better dependence. There's a very artificial problem that we would concoct where this exponential dependence was necessary. So that's the general idea here. I'll tell you a little bit about some of the ideas that came into this protocol. Both of which I think are sort of generally useful in thinking about it. In terms of compression, what really happened over here was a very interesting protocol that emerged. In the past, when we had perfectly shared dictionaries, I would send you a word which I thought was unambiguous. In the sense, I would look at all the other words which had all the other meanings that this word could take on given our dictionary, and say, well, all the other things look like they're low probability. Now what I would do is I'll not only look at this word, but look at every word which has a few spelling mistakes away, and make sure that none of them occur with high probability in your in our dictionary. So that's something that's also very natural. I mean, if you're giving a talk or in a fast conversation, the use of the word can't is something that I avoid. I typically try to say cannot, because I feel that there is a very small distance between can and can't. There's also a very small difference between now and not, which often leads to an ambiguous message. just saw this on a program committee discussion, somebody saying this can now be something, and I thought you meant not, and he said yes, 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 I meant not. So big difference between those two phrases. So you don't use short words when you realize that there is a chance that there is a nearby word which can mean something different. You can actually give meaning to that under this thing where our dictionaries are not identical but slightly noisy. The general protocol is also very interesting in that usually classical protocols for equality testing say take your message and produce some fingerprint, which would be like take some subset of the bits and produce the parity of the, tell you whether an odd number of bits are 0 or odd number of bits are 1. These kinds of protocols are extremely sensitive to the randomness. What subset did you use and what subset did I use? If we vary these subsets slightly, all bets are off. The new protocol for equality doesn't looks at the set of, we look at a subset of the bits. I look at a subset, I think this one. You look at a subset which is close but not the same. Rather than telling you the least significant bit of the number of ones in it, I'll tell you the most significant bit of the number of ones in this set. Okay? This is much more robust, and this immediately gives you a very robust protocol. Even if our sets are not identical, this is actually going to have a very good thing. On the other hand, if our strings are different, then we can actually make sure that it works out. Okay? So there's some nice protocols coming in. So finally, in the last 5 minutes or so, I'll tell you about the last vignette which we're interested in. And again, I'll try to tell you about both, there's this theme over here which is saying, firstly, we should be looking at communication problems under a different lens, not the Shannon lens of shipping the message over, because that's sometimes an overkill, but under the Yahoo model. So let me stress that again. So this is, by the way, it's a little late, but let me introduce the Yahoo model again. This is the model where Alice has some string x, Bob has some information y. They want to compute some joint function f of x, y. Let's think of it as Bob wants to compute this. So they go through some interaction. Either Alice sends a message over to Bob or they exchange messages. At the end, Bob should be able to spit out this function value. This is the kind of problem. This is a much better envelope for studying communication problems. And over here, we're always interested in the minimum number of bits. And of course, we're always looking at protocols where Alice and Bob share randomness. Now, one thing that I want to say, it's a bit of a digression, is communication complexity. It's been there since the 1980s. Been looking at it all this time. For the most part, when I look at the literature, they say, okay, here's this beautiful model. And page 2 will say, okay, now let me start proving that things cannot be done in this model. Okay? So here is a problem that takes n time. Here's another problem which takes at least n bits of communication. Here's a third problem. So I want to focus on communication complexity as a positive concept. And I really think, once I started thinking of it this way, I really felt I could look at lots and lots and lots of scenarios where this is the model that really captures what is going on. I want to design a web form. People are going to come in asking for different kinds of questions. I want to anticipate the questions, make sure that they click very few buttons and get the answers. What's the right model to study it? Some form of communication complexity. How many button clicks is some number of messages that are going back and forth between us? This is what I want to minimize. Many, many, many problems where I'd probably use this as the lens. I don't want to tell them all the things that I know in order for them to be able to figure out the answer to their question. They don't have to tell me all the things that they might possibly need in order to figure out the answer to the questions. We want to design a good interactive protocol. Communication complexity should be the lens under which we study it. So this sort of led to a work with Badi Ghazi and Pritish Kamath, which we are just writing about now. It's a taxonomy of simple problems. Once you say, okay, so communication complexity is an interesting problem, sort of like saying I come up with the Turing machine as an interesting model of algorithm, and then you start proving things cannot be done with Turing machines. But what can you actually do with them? So here's a small list of things that you can do with them. Here's a piece of work which you can hopefully look up, and you'll see some interesting things. And there's the unstated philosophical contribution of communication complexity, which is that if you have focused communication, it can be much more effective than unfocused. What does it mean to give focus to communication? We agree that we only want to compute f of x, y. Then communication can be very short and very brief. And in contrast, you might say, oh, look, I have X, I could send you the string, which will take me X units of communication, or maybe I compress it down to the entropy of this random variable, or maybe Y is sent over and then I send over the value of f of x, y, or maybe just the mutual information, or things like conditional information is what I should have, conditional entropy is what I should have put here. All of these things could have been measures, but all of these are vast overestimates in typical settings. Something much smaller is the actual communication complexity. That's what we should focus on. So if that's the thing, now again you could ask the same question. Focus helps communicating effectively. What if this focus is not perfectly shared? Okay, so what was the focus? The function. So I'm coming here, I'm going to prepare this talk. I would like to tell you some things. I'm trying to estimate what it is that you would like to learn. You come in here, you say, well, this is what I'd like to learn. Have we agreed perfectly on what is the function we want to compute? Certainly not. So maybe there is some way we can study this formally. So I won't go into the details, but we tried to study this. There's some formal models. Only thing I'll stress over here is that there are a bunch of questions that could be asked. We don't give answers, we make choices. Okay? Many of these modeling questions you don't make, when you have a question saying what should the model be, we don't have a definitive answer, we make some choices. We made some choices, and under these choices we came up with some analysis. It's a mixed bag. There are some positive results, some negative results. The positive results are of the following kind. If I have some information, some protocol where I send you information, the one-way communication format mostly explains what's going on today, and our private inputs are uncorrelated, which is very strange, then I can actually get away with imperfectly shared focus. On the other hand, if my private input is correlated with yours, we can come up with scenarios where large amount of communications is necessary. I mean, with perfect focus, I would have been getting through quickly. With imperfect focus, it takes a lot of communication. I don't understand what's the moral message of this result yet, but that's what we have. These are some of the results that we prove. It's in a paper with Ghazi, Komargotsi, and Kotari, and it's on my website. So I won't go through the results. I'll skip ahead to the conclusions. So first, I want to say that there should be a positive view of communication complexity, which is important. The context is a very, very, very important ingredient which we were traditionally swept aside. But in this interface of communication and computing, context, I mean, even when two devices are talking to each other, you cannot say dismiss the context. The context is there. What apps you've loaded on your phone influences how your phone will talk to my phone or to any central ingredient. What things reside on my laptop probably influence how it's working. So this context is extremely important, and it's it has various features. It is huge, but on the other hand, it is very essential to reducing the size of communication. And it's not perfectly shared. So we can't find any of the standards ways of dismissing it. So we really have to look at it explicitly and work with it. And there is a new notion of, for the theoreticians out here, I think in the past we would say, oh, look, at an additive factor of log n over here or there, I just don't care. Multiplicative factors, no problem, etc. In this case, the context is so large. What is my context for the lecture today? I would say every experience that my brain has ever registered. Same for you. From this point, how do we drill down to a small set of things that we choose to agree on? Is a process that I'd love to understand. It is a process involving communication and computing. I don't understand it, but there is something going on which is allowing us to communicate effectively, but we have to understand that. Log of this experience of mine is still a pretty long string. It's not something that I could dismiss. So we cannot throw away those log n factors. We really have to pay attention to how much is the communication and how much is it growing. And ideally, by looking at the uncertainty in the context rather than looking at the length of the context. And the good news over here is that there are many of these uncertainty problems where we can actually overcome the uncertainty. We can sort of circumvent the uncertainty without actually resolving it, which is, to me, very satisfying. We didn't have to agree on the function that we were computing in order to be able to figure out how to compute that function. We didn't have to agree on what was the distribution that the universe is producing messages from in order to be able to compress information. So when you can get away without resolving this uncertainty, I think it's a good news, and that's we are seeing some evidence that those things can be happening. But perhaps the most important thing that I want to say is there are many, many open questions and directions, and hopefully some of you will look at this. Okay. Thank you. Oops. Yes.
In your second result, did you imply that the length of a shared random string was a constant? The results depend on how.
Okay, good. So the question was how large is the amount of shared randomness? Typically, in the perfect sharing world, there is a result saying the length of the randomness needs to be only logarithmic in the size of the input that you're working with. In our case, we have no such results, and so actually, even though the original results might be working with relatively small amounts of randomness, much less communication, our results might actually use much more randomness, but it allows it to be imperfectly shared. So there's a trade-off. There's a very short amount of perfectly shared randomness that could work, or a large amount of imperfectly shared randomness, but the large amount of imperfectly shared randomness is not sufficient to give you a small amount of perfectly shared one. So we can't reduce to the original problem. So you really have to solve the whole problem fresh. Yes, question?
Have you thought about the connection between this theory and either humor or cryptography? So I mean, Turing is interesting, right? Because what was the enigma problem except trying to figure out shared context?
Right. So I mean, so one of the starting points for our theory was actually this work was apparently, I didn't know this, but or maybe actually we invited this. Somebody said, okay, these are the papers about talking to aliens. We really wanted to share meaning, and we do have papers which talk about what it means to share meaning and how is it that we try to arrive at a common understanding. Humor is a step beyond common meaning. I mean, it's a sort of a, but on the other hand, I think there's many processes associated with communication and in general, many aspects of cognition and human thinking and reasoning, where the philosophers and the linguists and the communication scholars have certain ways of talking about it, which are very intriguing in terms of revealing a phenomenon, but they are not precise in terms of saying what do they mean. Like humor is a concept. We all know what it means, except I don't see a definition anywhere. The opportunity is here. I mean, together between the theory of communication, the theory of information, we have all the tools necessary to start going around, taking up every one of these books in philosophy and saying this is what they mean precisely, or they're deliberately trying to confuse us between these two meanings, and that's why we can't make progress and understand the rest of the chapter, because there's ambiguity right there. So we do have the option of trying to understand every one of these elements. We try to understand what meaning was. How do we try to distinguish between a misunderstanding and understanding? That's as far as we got. And already it was getting to the point where all the theoretical computer scientists were trying to shoo us out of conferences. So we stopped there and then did other things. Neil.
I just wanted to come back to some of your motivating questions.
Sure.
Which were very practical and
right.
Everybody really cares about them. It seems like those helped you get into all these interesting
right.
questions. You haven't mentioned
going back to those things. Okay, so for the task like the printing, for example, we can, where it's interactive, we can suggest paradigms which might work. The paradigms would be interactive, but also have to have a setting where, so it has to involve ingredients of the form. I'll send something to the printer, and the printer will print something, and I'll look at it and say, oh, that was garbage. And this might have to happen a few times in order for us to be able to do it. The nice thing about this kind of a setting is that as my machine grows in time, as my machine grows with experiences and gets few user feedback saying that was wrong, this was wrong, it'll get smarter and smarter at learning and eventually get things down quite reasonably. And it also suggests ways in which the printers can be more effective in their communication with the computer, saying I won't just spit out all kinds of random things, reams of paper before actually testing something out. We'll do some things. You can learn from the small and try to grow to the big, etc. So there are lots of models, and there is a serious piece of work that we did about goal-oriented communication, which is one of the papers that I was citing. We do talk about it. Unfortunately, the solutions there are not remarkably creative. All that we think we're able to get to is a notion of saying this is what it means to misunderstand, and this is a kind of setting that seems to be necessary. This is the kind of primitive that seems to be necessary. It's actually that seems to be necessary, but it's not provably so, but is actually sufficient for you to be able to achieve common understanding eventually. So it's a very weak kind of a result. Nothing dramatic about it, but we do have such a thing. For non-interactive settings like publishing a book today and being able to read it 100 years from now or 1,000 years from now, we can prove negative results. Or we can try to say, look, you should make some assumptions on how much difference there is going to be between our civilization today and the civilization then. And maybe if you can we can propose measures of distance and say, if you're within this ball, then that person will be able to read it. This is the kind of mechanism that we could try to suggest. We don't even have a result suggesting it.
Okay, so let me make it another topic. Did anyone tell you about our synthesis requirements at UMass? Every PhD student has to do a synthesis between their field and some sort of rather different field. So I can imagine just a gazillion synthesis projects between this work and software engineering.
Right.
Actually building some things that would be pretty interesting.
Sure, right. I mean, I think within computer science, you can see many synthesis elements, but also outside of computer science. Economists are very interested in the notion of language and how communication works. And a lot of communication, I mean, you really have to understand it from the lens of the individual and saying, what is the individual going to get from this communication? If the individual cannot promise something for themselves, then they can be, fed a lot of random bits and they'll be pretty happy. So you don't want to get into that situation. So economics is very important. I mean, communication and media scholars, they have sort of such beautiful phenomena that they are capturing, and we don't understand what these are, and we don't have a formalism of what these are, and we don't have them in design products. These would be great to have. So, and certainly human computer interaction, I mean, there's a lot where, we would love to understand what are some good theoretical models around human computer interaction, which we could try to use to understand what are good interaction platforms and what are not. We're far from that. Okay. Sridhar, okay.
One thing that struck me was, I sort of remembered something from a long time ago. So Norbert Wiener was one of the founders of what we now call AI, but he called it Cybernetics. And I just looked it up, and it was basically what he called control and communication in animal and machine.
Right.
I think what you need is another word. This is not cybernetics, but it means computation and communication.
Right, but I think I already feel that. I mean, I think people were hinting at this problem from the beginning, and the problem that Norbert Wiener is referring to is probably the same thing. We are talking about the interaction between actions and communication, right, and the bits. So you're sending me bits and I'm taking actions on it, and we are trying to determine the correctness of understanding based on the action. So we do want to not assume that you and I have perfectly agreed on what action should be taken given a particular message. That is reasonable for a very limited set of circumstances and very unreasonable for almost everything else. And we would love to have settings where we can actually do this. So control, which is studying exactly almost the same thing, is very much part of the game. I think for it's a bit sad that information theory was left out of computer science for the longest of times, and we are slowly bringing it back, mainly because of machine learning, but also somewhat because of theoretical computer science. Control is another ingredient which has been somewhat far out. Robotics has been bringing it back into our fold, but it needs to be part of our field just because it is, we are controlling a lot of ingredients by sending bits around, and we really need to understand the process of control, the process of feedback, and the process of how to improve either the control or the communication. Okay, thank you.